Um, Thank you, Dr. Reddy, for those kind words of introduction and inviting me to give this webinar. And uh, good morning, good afternoon, good evening, and whatever the time zones that you are. Thank you all for joining this presentation on safeguarding our world, the role of remote sensing in monitoring critical infrastructure to prevent environmental disasters. So my hope through this webinar today is that you would be able to see the application of remote sensing, particularly satellite-based remote sensing, in monitoring critical infrastructure that we have. So in this presentation, I will actually show two examples or two case studies, but hopefully this will give you some ideas of how this technology can be utilized for some of the other critical infrastructure and needs that you are facing in your context. So with that, let me begin with the picture of the 2019 Brumadinho tailings dam failure in Brazil. This happened at an iron ore tailings dam. I believe most of you are familiar with this. It created a huge problem in that region. Almost 125 hectares of forest land was lost, which is equivalent of more than 1 million square meters, or around 125 soccer fields. And today, we have around 18,000 mine tailings dams around the world that are not monitored continuously, and that could, with the increase in precipitation and the climate change factors, that could be a challenge to monitor these tailings dams and to ensure that they don't result in situations similar to what we have seen in Brumadinho. Some of the other things that to consider is the accidents that happen along the rail corridors. You can see here, since 2013 in North America, there has been 21 oil train accidents alone, where train derailments have caused oil tankers to catch fires, spill oil into the surrounding environment, and lead to very, very costly cleanups. And when you actually look at these, be it the Brumadinho mine tailings dam failure or some of these train derailments, the common factor that you see here is the ground often is either settling or moving, which is causing the infrastructure to fail. So understanding the stability of the ground where this critical infrastructure is placed is very, very important. This is a picture of a very recent event that happened in US, in East Palestine, in the state of Ohio in US, where tankers carrying several types of chemicals ruptured and caught fire, and had led to a very serious environmental concern in the region. Now, if ground is a common factor here, and the ground movement or ground settlement is something that needs to be studied, I just want to point out to you on the right, top right, the map that you're seeing is the map of all the transportation main primary and secondary network in the US. And the ones shown in red are the areas where there is high susceptibility for landslides. So ground movements, landslide susceptibility is pretty high in some of these regions, and any of those landslide activation can interrupt these transportation corridors, be it highways or railways, and it can lead to bigger environmental concerns when these corridors actually carry chemicals, oils, and things that are, in case of a spill, can be very dangerous to the community. On the bottom right corner, what you're seeing is the major dams in the United States, 8,100 major dams. And if you actually overlay the landslide susceptibility map on those, you can see many of the dams are also vulnerable to landslides and ground movements. On the left top, you can see the levees in US. Again, very similar situation. So critical infrastructure is vulnerable to ground movements and settlements in the US, and they need to be monitored. With the aging infrastructure, if you look at the infrastructure in the US, you would see that most of, or a majority of them, have passed their design life. So with the aging infrastructure, the uncertainty that we have over climate change, and the increased extreme rainfall that we have been seeing, build and forget is not an option for us in terms of critical infrastructure. Well, if build and forget is not an option, what is our option? Our option is that we need to have performance monitoring. We need to actually monitor these infrastructure after we build. We cannot just forget about it and just expect that it would function forever. So performance monitoring helps us to characterize the site condition prior to design, monitor construction activities, monitor performance of a structure over its lifetime, compare design assumptions to actual loading conditions and see if they are functioning as per the design, and identify problems before they lead to failure so that we can actually build community resilience in the process. So performance monitoring is a very important step. Now, I hope through these series of slides, I have convinced you that critical infrastructure needs to be monitored. And if the critical infrastructure needs to be monitored, how do we do that? And the traditional approach is to use inclinometers, tilt meters, extensometers, settlement cells. So all of those tools that geotechnical engineers have been using for several years. That's the traditional approach. And this approach is quite successful. We do get very reliable values from this, but when we have such extensive network of critical infrastructure, as shown in this map, where there is a lot of transportation corridors that are vulnerable, there is thousands of dams that are vulnerable, and then think about other critical infrastructure like the tailings dams and all of that. When you have that extensive network of critical infrastructure, is the traditional approach sufficient? That's the question that I want you to think about. Can we still utilize the traditional approach, or do we need something more? And that is where I want to actually make a case that remote sensing can be an opportunity here to be able to monitor these critical infrastructure. Not as a replacement to traditional approach. I still see that the traditional approach have a big role to play, but at the same time, the remote sensing can be a complementary information to kind of identify critical regions and then you could use a traditional approach to monitor those critical locations. So that's my thesis here. So let me actually walk you through some examples. And before that, what do I mean by remote sensing here? Just for the term remote sensing, what I'm referring here is for different types of sensing using the electromagnetic wavelengths. Some of the common methods that are used right now are InSAR, which stands for Interferometric Synthetic Aperture Radar, LiDAR, light detection and ranging, photogrammetry, thermal sensing, multispectral, hyperspectral. And these sensing can be done from different platforms, be it a satellite platform, aerial platform, both manned or unmanned, terrestrial platforms, which are stationary or mobile. So there is different ways that you can actually carry out remote sensing. But due to the constraints of time, in this presentation, I will actually focus on two case studies that are specifically from InSAR with the Interferometric Synthetic Aperture Radar, how InSAR can be utilized. And I will actually give you a very brief idea of how the InSAR technology works. So, as I said, InSAR stands for Interferometric Synthetic Aperture Radar, and the SAR, which is the SAR part, which is Synthetic Aperture Radar, works by illuminating the Earth with a beam of coherent microwave radiation similar to laser. So InSAR is an active source of remote sensing where there is a coherent microwave radiation is being sent to the ground, and the return of that is recorded as amplitude and phase. So it's a complex number that is being recorded, both amplitude value and the phase values there. And when it comes to SAR, there are different wavelengths that you can actually do the SAR. There is X band, C band, L band. Those are some of the common ones, but there are other ones too. And when it comes to these bands, the key thing that you need to remember here is the X band is 3 centimeter, the C band is 6 centimeter, the L band is 24 centimeter. And the wavelength has a big role to play in terms of how large of a ground movement you can actually detect. So I will explain that as we progress here. So just remember that there is different types of synthetic aperture radar wavelengths. X band, C band, and L band are the common ones, and the wavelengths are 3, 6, and 24 centimeters. So here you will see a cartoon of how this technology works. So for example, you have a first acquisition of the satellite. It took the range and the amplitude value. Say by the second time the satellite came through, the ground had some movements and there was some settlement. So the range of the radar back, the return has changed. So between R1 and R2, there is a change in range, and what we are basically trying to do is trying to detect that change in range from the satellite. Now, you might be wondering, can we do that? Because the changes on the ground are not as dramatic as what I have shown in this cartoon, where the ground is settling several feet. There is only centimeters and millimeter scale of movement. Can you do that from a satellite that is 800 kilometers away from the ground? And the beauty is, yes, we can do that because we are measuring these wavelengths in centimeter scale. And because of that, we do have millimeter scale accuracy. And those of you who are interested in the math or how this works, you can see the change in range is a function of the wavelength and the phase. So you're measuring the phase difference, And because you're measuring the phase difference, and you can only measure half the wavelength of displacement that is happening at the site. So that is where the wavelength of the satellite becomes an important factor. So if you remember, X-band has 3 centimeter wavelength. So what that means is if you're using an X-band satellite, you can only detect up to 1.5 centimeters of ground movement. If you have movements larger than that, you will have a decorrelation, and you will not be able to really measure or quantify how much movement has happened. You can only say that there is some kind of disturbance that has happened, and I cannot actually quantify that. So that is between two acquisitions. And these satellites, in the most case, there is every 2 weeks. So if there is more than 1.5 centimeters of movement between 2 weeks, probably that is something that can be easily detected with visible approaches. But so the InSAR is really good to identify small scale movements, small scale creep or cumulative movements that are slowly building up. InSAR can be very useful. But if you want to actually detect some of the larger movements, you might want to utilize a wavelength like the L band, which has 24 centimeter. And that gives you a 12 centimeters of detection. And as I said, currently, most of the data that is available is around 2 weeks of time, temporal resolution. There are commercial satellites being launched right now, and in the approach that they are proposing is to have every 4-hour monitoring of the entire globe. So that is where the technology is moving to. With around 60 satellites, they are able to actually cover the entire globe and provide 4 hours of coverage. So in the future, we would have a much higher temporal resolution to be able to utilize some of this technology. So with that basic guidance on how SAR and synthetic aperture radar works, let me quickly show you some 2 case studies where we have utilized this concept. The first one, we are using the Advanced Synthetic Aperture Radar sensor on the NVSat mission that was launched by the European Space Agency. This mission was from 2002 to 2012. 23 NVSat images were acquired from 2005 to 2010 period. And the spatial resolution of this data was about 20 meters. And in this case, the wavelength is about 5.6 centimeters specifically. So if the wavelength is 5.6 centimeter, the displacement that we can actually detect is around 2.8 centimeter between each satellite acquisitions. So here is the work that we did from that in the California, particularly in the Palos Verdes Peninsula, where there is a large amount of landslides happening or ground movement occurring, reactivation of some of the old landslides. And what you're seeing here is the overlay of the PS InSAR persistent scatter in interferometric synthetic aperture radar points on a satellite image, so that you can see the velocity values. So we are actually calculating how fast these points are moving. And if you look at the legend, let me just walk you through this legend here. You can see what we are showing on the legend is points that are red are a negative 2.8 standard deviation or greater, and points that are dark green are positive 2.8 standard deviation or greater. The colors closer to yellow are ones that are close to the mean. And what we are looking at is what is the mean movement at this location in this area. So just to give you a reference here, I have the scale here at the bottom. This area is about about 10 kilometers to 6 kilometers, so about a 60 square kilometer area. And in this area, we had around 600,000 points where we were able to measure the ground displacement. So for the geotechnical engineers in the call, if you had to install 600,000 inclinometers in a 60 square kilometer area and measure the ground displacement, you know what a nightmare that would be, right? To be able to make sure all of those 600,000 inclinometers are working and getting the data and making sense of that. That's going to be a really difficult task. But that is what the InSAR technology provides you. Very high resolution look on the ground without the cost of maintaining all this instrumentation and being able, without having to install, you're able to actually get an overview of an area, how this area is performing. Now, in this, you can see there are some areas where the points are red, which shows that there is ground moving away from the satellite or settlements happening there. There is oil wells and pumping happening in this region, and we believe some of that is tied to that. There are also some regions where you don't have points. There is, if you are able to see my mouse, you should see that there are areas where there is no points in between. Those are areas where there was decorrelation. We don't know whether it is more, whether it is movements that exceeded half the wavelength, or whether it is due to some other factors like vegetation and things that are decorrelating. So you do have some of those limitations. Particularly in this southern portion, you have several regions where you don't have points, and we know that this area doesn't have vegetation. And what we have, and this is an area that has a lot of landslides happening that are fast-moving landslides. So this, we believe, is a result of those fast-moving landslides. Now, when we did this large analysis, particularly one area stood out to us, which is located in Ventura County, about 100 miles northwest of Los Angeles. So, and this is a dam location, and that's the Citas Dam in California. This was built in 56 to 59 time period, operated by the U.S. Bureau of Reclamation. And the crust length is roughly about 2,000 feet, crust elevation about 600 feet, and berm height of 130 feet. And you can see the dam here. There was a berm built to stabilize this dam, and that was done in the 90s, around 2000, and that was a 42 million retrofit of the Citas Dam. Considering the seismicity of the area, they felt that there was a need to further stabilize this dam, and this berm was constructed. And what we saw from our InSAR analysis was that there were some movements happening on the dam. So we actually plotted across the crust 4 points to see what is happening. And what we saw was a point 4, which is the yellow color, did not have a whole lot of movement from 2005 to 2010. Point blue and point gray, which is 1 and 3, were performing similarly. There were about 10 to 15 millimeters of movement over a 5-year period. So again, very little movement or within the noise levels. But point 2 showed much higher movements. You can see about 45 millimeters of movement in that 5-year period. The question was, what was happening at point 2 is that of concern. So we started doing some both spatial interpolation of that points over time period so that we can actually temporally see how those displacements were forming. And you can see where the berm was constructed, there is this movements happening. And as the time progresses from 2005, now it is 2007. And as you progress, you can see slowly the movements building up at that location. So you are able to get more both a spatial and temporal view of what is happening at your critical infrastructure. And what we saw was that maximum displacement at the crust was about 22 millimeters. The berm had higher displacement values, close to 32 millimeters. The berm was newly constructed. And when we look at high resolution satellite images, we can actually see visible failure at the crust. So this is a 336 feet slope, and you can see that there is flow and cracks developing at the crust, and you can actually match that very well with the InSAR displacements. At the same time, on the berm part, we could not actually identify any visible failures. So it is more a failure that is not as expressed on the surface. It is more subsurficial failure that is going on at the berm. So this is actually the beauty of the InSAR technology. You can not only identify the ones that are visible, but also the ones that are happening in the subsurface, but probably not visible to the naked eye. If you look at the guidance for monitoring some of the dams, you can actually see the guidance is that for existing embankment dams, settlement of the crust or bulging of the slope might indicate developing problems. So here you're able to utilize InSAR to identify developing problems early on. And the recommendation is horizontal and vertical surface movement of proposed embankment dams should be monitored. One line of measuring points along the crest of an embankment dam is usually sufficient, and measurement points should be spaced sufficiently close to allow measurement of all significant deformation. So 5 to 10 measuring points are typically sufficient. And you can actually you can meet those standards with the InSAR technology. And this is the guidelines for the evaluation of hydropower projects provided by the Federal Energy Regulatory Commission. Let me quickly also walk you through another example where a critical rail corridor between California and Utah, which carries carries oil and chemical, has shown some vulnerability to landslides and ground movement. And we were asked to take a look at this issue. The agency reported that from December 2005, they saw some movements on the slope. And in 2011, there was a massive rock slide that happened. The question was, what is going on here? Can we actually detect these from the satellite remote sensing? So we utilize the concept of interferometric stacking from 2 different satellites in this case. The ERS, which is from August 1992 to 2000, and the NVSAT, which is from 2003 to 2010. And here, the benefit is both the satellites had very similar, or they had the same imaging characteristics. So you are now able to actually combine the data from this and process it together and look at a historic perspective for a long time. So not only now you have the ability to get this very dense observation of ground movement, you also have the ability to go back and look historically how it has performed. So often when we have projects or when we have a new development project, we start putting monitoring systems to understand how the site is performing, but you don't have the luxury to look back, okay, for the last 10 years, last 15 years, how did this site perform? And this is going to be very critical considering new developments in hilly terrains and areas where there is higher vulnerability to landslides and things. When there's major projects happening, it would be critical for us to go back and look how this area has performed over time. So in this case, we processed the data from 1992 to 2010, so roughly about 10 years, 20 years of data. And what we found was at the site where the ground is failing, there is higher displacement, so close to 6 millimeters of displacement compared to other areas which are much smaller. So the question was, what is going on? Why is there 3 points very close that show high displacement near the failure? And when we plotted that data from 92 to 2010, what we saw was till 2005, those points were stable. There was no movements happening till 2005, which the question was, why in 2005? Was there an earthquake? Was there any kind of event there that triggered this? So we started actually digging into the seismic data, the weather data, all of that. And what we found was in 2005, you can actually see stamped date photographs. On January 12th of 2005, there was a major flood event that happened along this corridor, which led to derailments, and several trains were derailed, train cars. And you can see, in order to put the track back, the company came and did blasting of the slope top, the top of the slope, and they got the material to put the track back quickly. So now by doing those blasting, they have actually created unstable slope in this region. So now you can see how well the InSAR technology can be utilized for a forensic investigation kind of approach. And then when we presented this result, the company asked us to go back to that entire corridor and see if you can identify other areas that they need to be concerned of. And we did that, and we found several other locations that they have problems and that would lead to more catastrophic failure. And we made those recommendations. And they actually started fixing some of the locations. You can see they actually did shotcrete to stabilize the slope and so on. So here you can actually see how you can even do forensic kind of investigations and make recommendations for the future. And this same approach can be used for new development. You can actually see how the area have performed over a long time, and what can be done to, if there is new developments coming, which areas you need to select and things like that. You can utilize this technology. One thing that I want to point out to you, those who are interested to utilize this technology, it is going to be an exciting time in the coming years. The NASA and the Indian Space Research Organization, ISRO, are jointly launching an S and an L band SAR mission, which is called the NISAR mission. It is planned for 2023, but it is now, the launch date is pushed to 2024, but it is coming soon, and it is going to have global coverage, rapid data delivery for hazard monitoring, and it is specifically designed for InSAR. So for those who are working in this area, this is going to be an exciting time. So if you're interested, you might want to take a look at this technology and see how you can utilize this for some of the other areas that you're working in. So with that, I want to summarize some of the conclusions that I have particularly presented to you regarding the remote sensing, utilizing the InSAR, the interferometric synthetic aperture radar. There is a rich data archive for forensic investigation. Millimeter scale movements can be observed from satellite platform using stacking techniques, provides an opportunity to proactively monitor infrastructure, and improved spatial and temporal resolution is available. So I hope I have convinced you that critical infrastructure needs to be monitored. Building and to build and forget is not an option. The traditional monitoring has a role to play, but when it comes to large networks and massive amounts of critical infrastructure, we do need more broader approaches that can look at this in a larger scale. And that is where I think the remote sensing is going to play a big role. And with that, I want to thank the team that has been working with me and the agencies that have funded my research. Without their support, without my postdocs, my graduate students and collaborators, none of this would happen. So, and I want to thank the agencies that have been supporting my work. With that, thank you all for listening, and I'm happy to take any questions if you have, and I'll flow back
Thank
to
you
Dr. Reddy.
thank you very much, Professor Oommen, for a very interesting